Okay, this is section 3 of chapter 8, the law of cosines. We have the formula for the law of cosines: c squared equals a squared plus b squared minus 2ab cosine c. Notice that on here, the angle you're taking cosine of and the side length on the other side of the equation are opposite of each other. So if you were to say, be looking for side A, if you had a squared over here on the left, then you would need to have cosine of A over here. So the side on the left has to be opposite the angle on the right. The way I remember this law of cosines is, if you think about it, we have Pythagorean theorem says that's A, B, and C. A squared plus B squared equals C squared. Okay, that's the Pythagorean theorem. If I take this triangle and I just move this side in a bit, we'll still call this A, B, and C. We've changed the length of C now and moved it in so that it's smaller. So it's kind of like taking, okay, A squared plus B squared, but now we're taking off a little something. So it's minus a little something here. And that little something is represented by that term 2ab cosine C. Consider, if this were 60 degrees right here, cosine of 60 degrees is equal to 1/2, and so what I'd be doing is subtracting off 2 times the lengths of AB times 1/2, and so I'd be taking that off to get my new length of the side there. So that's what we're doing with the law of cosines. If I had an obtuse triangle here, I would actually end up extending C, and so if this were A and this were B, we have A squared plus B squared plus a little something. And so consider, well, if I had a 120 degree angle right here, 120 degree angle, if I take the cosine of 120, I get negative 1/2. That negative 1/2 with the negative in the formula will change that to a positive and add something to the length of C. So that's the law of cosines. You're welcome to look up in the book the proof. The proof is based on kind of a similar triangle that I had shown you for the law of sines, and then labeling it, and then using the distance formula to derive the law of cosines. And so that's in your textbook. You could look through that if you'd like. This is the law of cosines. It's the third and final method we're learning for solving triangles, so finding all the side lengths and all the angles. So look at number 1 here. Number 1, we have, just going to draw my generic triangle. We just have an angle of 40 degrees. Let's put that up here. We've got, we'll call this B over here. This is angle B, we have angle A over here, 12 over here, C over here, 20 over here. Not to scale, I just drew my generic triangle without really thinking about the scale here. But we go through, we use the law of cosines, set it up to find our missing side length B. So since I'm finding B, B squared goes on the left equals 20 squared plus 12 squared. We use the law of cosines in a side angle side case, so we have an included angle between two sides. The 20 and the 12 are the sides on each side of the 40 degree angle. So minus 2 times 20 times 12, and then cosine of the angle opposite the side we're trying to find is 40 degrees. So we go ahead and calculate this. We got B equals the square root of this term over here on the right, and so B is equal to the square root of 20 squared plus 12 squared minus 2 times 20 times 12 cosine 40 degrees. You just type that in your calculator just as you see it. Make sure you're in degree mode, and we get B equals 13.3. All right. Next thing you're going to do is, now to find the other two angles, we're going to need to use law of sines. And we need to be very careful here. If, as a matter of fact, if you choose one angle over the other, you kind of have to test it. It's possible to not get the correct triangle here, or to basically we have to check for the ambiguous case, because what we're doing is creating a side-side angle scenario in which you could have 0, 1, or 2 triangles. So you could potentially end up with an angle for, say, C or for A that wouldn't work in the triangle, wouldn't make sense in the triangle. So if we go with finding angle A, we go sine, so we have sine of 40 degrees over 13.3 equals sine of A over 12. And if I solve that for A, I get A equals 35.4 degrees. I want to test that. 180 minus 35.4 gives me 144.6 degrees. You can see that based on this information, we only have one possible triangle. If you look at the 144.6 plus the given 40, that's bigger than 180. So there's only one triangle possible here. And by finding A first, I found that one possible triangle. That's 35.4 for A. And then that would leave me an angle C of 104.6. And my drawing is completely bogus, or not to scale, but there it is, 104.6. But what we do see here is opposite the biggest angle is the biggest side, opposite the middle angle is the middle length side, and then opposite the smallest angle is the smallest side. Now what we noticed in fourth period, which you might want to just observe here, I want to show this to you, is that if I had gone and found angle C, here's what happened, sine of 40 degrees over 13.3 equals a sine of C over 20. And if we go ahead and calculate C in this case, we get, I'll have to go ahead and do that, I'll show you what it looks like. It's 20, so it's inverse sine of 20 sine of 40 over 13.3. So it's inverse sine, I think I have it up here somewhere, maybe not. Okay, so second sine of 20, I'll go back and look, I forgot what I was typing in. It's 20 sine of 40 over 13.3. So 20 sine 40 divided by 13.3. We get 75.1 degrees. So go back over here. I'll show you what's going on. So we get C is about 75.1 degrees. If we do our test here, do 180 minus 75.1, we get 104.9. So 180 minus 75.1 gives me 104.9. And so
I'll just wait until when class starts.
Okay. So if you got a 75.1, watch what happens here with that 75.1. So I draw my picture again here. So say I found C first as 75.1. And then that would mean, well, B is still 40. Here's B, here's my 75.1 at C. This is 12 here. We got the 13.3 here. And that would leave me with, there's 110, 115.1. So that leaves me with an angle of
the makeup
of 64.9 right here. And you can see there's a problem with this. If this were 20, so the 20, the 12, and the 40 were all given to me. Can't change those. But say I found angle C first at 75.1. What you'll see here is that we have a little bit of a mix-up here in terms of the triangle, kind of the way in which triangles are set up. We can see that the 75.1 is the biggest angle, and it's opposite the biggest side. We're okay there. But then we have a little confusion going on here. We have a 64.9 opposite the smallest side, when in fact the 40-degree angle is the smallest angle. And so in observing this triangle, we see that that 75.1 for C is not going to work. 75.1 for C is not going to work. And so C cannot equal 75.1. When we did angle A, we saw that when we tested it, that it was only possible to have one triangle. This is a single triangle case. And so the single triangle is what we have found when we found angle A first. So you'll have to test it, make sure that you don't get something that isn't going to work. So, second problem on here, this is a side-side-side case. And I'm going to just draw my generic triangle, not think about it here really, and start labeling the sides. So I have let's see, I can put the 10, that's C, and then A, it's over here, 8, and then B is 5. And so what I'm going to do is use the law of cosines to find the angle. I'm going to find angle C first. So I have C squared. Let me write down the equation first. It's actually C squared equals A squared plus B squared minus 2AB cosine C. That's my law of cosines equation. We can actually solve this for the angle C and then go ahead and plug everything in. It would look like this. I would subtract over the A squared and the B squared. And then I would divide through each side by the negative 2AB. So it will look like this: C squared minus A squared minus B squared all over negative 2AB equals cosine of C. And then finally, inverse cosine of this whole mess here, C squared minus A squared minus B squared all over negative 2AB has to give me angle C. So now I've solved that once and for all for angle C. Okay, so now we just plug in everything we know here. Move this down a bit. So plug in everything we know. This is inverse cosine of 10 squared minus...
Perfect day.
Okay. Alright, we're recording this at lunch, so every 2 minutes we have an interruption here. So it's 10 squared minus... what was A here? Minus 8 squared minus 5 squared over negative 2 times 8 times 5, and that will give me C. So if you go ahead and calculate angle C on your calculator, you will get 97.9 degrees. So C equals 97.9 degrees. Okay. Then we need to go ahead and use law of sines. So I would just go ahead and do law of sines with that the angle I just found. So sine 97.9 over 10 equals, we'll find A first, sine of A over 8. Solving for A, we end up with 52.4 degrees. And once we have A and B, A and C, we can use the fact that the three angles add up to 180 degrees to go ahead and find the third angle. So 52.4 degrees, and then the last angle is 29.7 degrees. Alright, so we've solved that triangle. We found all three sides. If we had tested this angle A that we found, 180 minus 52.4, would give me an angle that when combined with 97.9 would be well over 180. So just one single triangle possible here. Alright, let's go on to number 3. It says a boat leaves Naples, Florida, bound for Key West, 150 nautical miles away. So we might start here at Naples. We head into Key West. 150 nautical miles away. The problem is they get off course by 20 degrees. And they're off course for 4 hours. 4 times 15 nautical miles per hour gives me 60 nautical miles that they're off. So that's 60 right there. We have our little boat right here. Way off course. We've got to find out what angle measurement he needs to turn through to get back on course, and also how far X he needs to travel to get to Key West. So part A, we're going to find out X first. So that's how far the boat is from Key West. So that'll be, let's go ahead and use our law of cosines. We'd have x squared, or x, equals the square root of 60 squared plus 150 squared minus 60 times 150 cosine of 20 degrees. Plug that into your calculator, you get about 95.8 nautical miles. Way off course, 95.8 nautical miles right here. And so the second question, part B, is, what angle does he have to turn through? Here he is up here. He's heading in this direction. He's got to turn through a certain angle here. Looks like it would be an acute angle, because this angle right here is obtuse based on my picture. So, of course, we have an ambiguous case here. There's 2 different possibilities.
Matthew?
All right, so what angle does he have to turn through? We've got law of sines we got to use here, and we're going to go ahead and set it up. We have sine 20 over the new side length I just got, 95.8, equals, we're just going to call it sine of theta over 150. And then when I go and calculate theta here, theta is about equal to 32.4 degrees. So just because of the ambiguity here, it could be that, if this had been, the triangle looked a little different, maybe he'd be turning through the supplement of this. In this case, we can tell because this length over here is just 60, this one's 150, I have a fairly accurate picture. He's got to turn through this acute angle over here. And so what we've actually found is this outer angle, which is the 32 degrees, and that is the degree he needs to turn through to correct his course. As a matter of fact, the complement of that 180 minus 32.4, which is 147.6, is what my angle in here is. That's the 147.6 degree angle in there. Part C is asking, once the turn is made, how long will it take to get to Key West at the same 15 knot speed? Well, he's got to travel 95.8 nautical miles at 15 knots per hour, so that gives me about 6.4 hours. 6.4 hours for part C. So draw a picture. If, like I said, if this had been something like this, something like that, so he's going on this course, say this were the 60 and this were the 150, we'd have a different case here. Here's my boat here. You'd have to turn through this obtuse angle, this angle that's more than, let's see here, more than 90 degrees for sure, but we have to turn through that supplement of the 32.4 if that were the case. So just pay attention to the picture, what's happening on there, and make sure to get the right angle there, just because of the ambiguity that comes with using law of sines with finding the angle. All right, so here we have a baseball diamond. We've got right here is 280. We've got the distance from here to third base we're going to find. We've got the distance from third base to home, which is 60. We know if we split this 90 in half, we've got a 45 degree angle here. So I might want to pop that out here. Here's what we have. 60, 280.
Will the following students please report to the attendance office? Jaime Cortez, Kai Schaefer,
45
Fergus
here.
Day, and Joseph Russell.
And we're going to find x. So we have x equals the square root of 280 squared plus 60 squared minus 2 times 280 times 60 cosine 45. And x is about equal to 241.3 feet. So just a basic law of cosines. We've got a side angle side case. My side, my angle, my side. And we're finding that side opposite the angle of 45 degrees. All right. It says, assuming the circles are tangent, find the lengths of the sides and the angle measures of triangle ABC. Let's draw triangle ABC first of all. So this triangle ABC, we have this length right here is going to be 15. That goes from C to B. It's just putting together the two radii. This other one from A to C is constructed of, well, the radius of 7, and then we also know that the radius of the big circle here is 20. So 20 minus 7 is 13. It might help if I made that little radius from A out there just extend out. And then if I did the same thing over here, we'll see that we have 20 minus 8, which is 12 right here. So we have our three side lengths. Those are taken care of. We're going to now use the side case and the law of cosines to find A. So we know that A is equal to, by the formula we solved earlier, inverse cosine of the side opposite A, 15 squared, minus the squares of the other two sides, all over negative 2 times 13 times 12. It's a 12 there. And A is about equal to 73.6 degrees. Then we could do a quick law of cosines calculation, sine of 73.6 degrees using this angle here, which is opposite the 15, and set that equal to sine of B over the 13. B ends up equaling about 56.2. 56.2. So if B is 56.2, then C, we can tell from the picture, it looks like it makes sense. 180 minus 56.2, if I took that angle, whatever that is, and combined it with 73.6, I'd get something bigger than 180. Just checking here for our ambiguity. But C is equal to 180 minus the sum of those two, which should come out to be 50.2 degrees. And you have solved for that triangle. I hope this helps.